time independence perturbation theory has real-world effects that can be studied, including in regards to the Zeeman effect and Stark effect, used in regards to energy splitting in atoms and molecules and the like. Starting with what time independence perturbation theory really is, it involves taking some known system, some solvable system of the Schrödinger equation, where it's possible to apply the Hamiltonian on some wave function and receive the total energy eigenvalue. For many situations, however, it's impossible to solve the real Hamiltonian or the real Hamiltonian of some system due to the complexity of the quantum mechanical system at play. So instead, perturbation theory is simply starting from some known solvable system, slowly adding perturbations, some slight additions or adjustments, until we can more accurately model or approximate the unsolvable system. So in other words, H naught of psi naught would be the wave function with a solvable Hamiltonian that can get a exact total energy, E naught. And then for the unsolvable system that needs to be approximated, the Hamiltonian of that unsolvable wave function can be approximated by taking the Hamiltonian as the summation of the solvable system plus some slight perturbation in a Hamiltonian multiplied by some parameter, lambda, that is between 0 and 1. And it doesn't necessarily need to be just adding one perturbation. It could be multiple. If we added 2, it would be lambda h prime times lambda squared h prime, so on and so forth. Real cases for using time-independent perturbation theory can be used for seeing energy splitting when we have energy levels in an atom or molecule that may be degenerate. Applying certain situations, subjecting that atom to certain situations, can resolve in those degenerate energy levels actually becoming distinct and split. And two of them are really just looking at whether we apply a magnetic field across our molecule atom ion of study, or we apply an electric field. Many atoms have a magnetic moment, and when applying a magnetic field on that substance, the change from degenerate energy levels to energy splitting by applying a magnetic field is the Zeeman effect, whereas applying an electric field for a substance with an electric moment, that is what results in the Stark effect. So these perturbations, looking at the Zeeman effect and the Stark effect, those are really perturbations to the Coulombic Hamiltonian. Therefore, we can approximate the Hamiltonian, a new Hamiltonian, by taking the easily solvable Coulombic Hamiltonian and then making a slight perturbation through monitoring the Zeeman effect or monitoring the Stark effect, which again is just if we apply a magnetic field to a substance with a magnetic moment or an electric field to a substance with an electric moment. And something like hydrogen has both of those moments, so it's possible to look at both of the Zeeman effect and Stark effect. Now, just as some example of energy splitting, one possible example, there could be when a magnetic field is not applied and the Zeeman effect is not shown. There could be just some degenerate 3D energy level, set of energy levels, and an electron can transition from there to the 2p, any energy level in the 2p's. But when applying a magnetic field, those energy levels can split, where we see our distinct 5 shells for the 3D orbital, and the 2p breaks up into the three orbitals. And likewise, uh, just as with the Zeeman effect, when a magnetic field is applied, it's also possible to apply an electric field, which in the case for a hydrogen atom, applying an electric field also helps distinguish those originally degenerate energy levels, splitting them into individual orbitals.